With a lot of the basics out of the way, let's explore some advanced typing concepts now. Some advanced concepts TypeScript offers to you that can become handy in certain situations you might be facing in the projects you're working on. In this module, we'll have a look at a couple of interesting concepts, among them intersection types, what that is and why it might be useful, type guards, what we can do with those, discriminated unions, fancy term for a quite interesting topic. We'll also have a look at typecasting, a useful feature for telling TypeScript about the type of something in cases where TypeScript is not able to find out which type something has on its own. And we'll have a look at function overloads, a pretty neat feature that allows us to write more flexible functions with better TypeScript support than we might otherwise get it. For this, I'm back in the general project setup we worked on before. You find it attached, empty index.html file, empty app.ts file. And in there, I want to dive right in with intersection types. Intersection types allow us to combine other types. Let's say we have a type, admin, which is an object type. So again, this is not creating an object here. We're defining a type. So I'm just defining a type definition here. And admin should have a name, which is a string, let's say, and an admin should also have privileges. And that should be a string array, for example. Now we could have created this with an interface, but here I am doing it with a type. And now I have another type, a general employee type, let's say. And there I also have a name, string. I have no privileges, but I have a start date. And that could be of type date. We haven't seen that before, but date is a type that is supported by TypeScript based on the date object that is built into JavaScript. So now we want to create a new type here, an elevated employee, let's say, which should be the combination of these two types. Now, of course, we could create it manually by simply defining an object type which has a name, which has a start date, and which has privileges. But if we have these two types already, then we can also just combine this by saying admin and, so we use the ampersand symbol here, employee. And now the result is a new object type which must have both. So if I have my employee E1, which should be of type elevated employee, then I can store an object in there which must have a name property, which must have a privilege property, create server, and which also must have a start date. And with new date, I create a new date object, which simply is the current timestamp. So this is now a simple way of combining two types. Now I will say that intersection types are closely related to interface inheritance, because of course we could have achieved the same here by using an interface admin and then an interface employee, and then we could also use an intersection type on these interfaces, or we create a third interface, elevated employee, which extends employee and admin. And therefore, if I now comment this out, we would have the exact same effect. Now, arguably, that's a bit more code. One reason why we maybe would prefer to use types here instead of interfaces, but the relation definitely is very close, and you could absolutely use interfaces for this example. However, it is worth noting that whilst intersection types can be especially useful when used in conjunction with object types, as we're doing it here, you can use them with any types. So if you had some other type, combinable, let's say, and that's either a string or a number, so we have a union type here with the string or number base types, and then we had a numeric type here, which is either a number or a boolean, well then we could have our, let's say, universal type here by intersecting combinable with numeric. And in the end, TypeScript then sees that universal, of course, is of type number because that is the only intersection we have here. But if you had more intersections, then this would be the type that is assigned to universal. So that could also be a union type, which is the intersection of these two union types. So the intersection operator can be used with any types, and it then simply builds the intersection of these types. In the case of a union type, that is basically the types they have in common. In the case of object types, it's simply the combination of these object properties, so to say. So these are intersection types. Can sometimes be useful. You'll not use them all the time, but you definitely can encounter situations where you can express something in a simpler or shorter way by using intersection types. Now, just to prove that this also all works, let me open up a new tab here in my terminal and run tsc-w to start the watch mode so that I don't just have the ongoing live server, but I actually also build my code. Now, if I reload once here, we see this runs without errors, and it also compiles without errors. Now, intersection types are one thing. Used more often, however, is another feature, and that would be type guards, a feature we actually already used a bit. Let's use combinable here. It's a union type where we either have a string or a number, and type guards help us with union types, because whilst it is nice to have that flexibility, often you need to know which exact type you are getting now at runtime. Let's say here we have our add function where I get a number which needs to be of type combinable, so a string or a number, and therefore I'll actually name it A here. And then I got another argument which also needs to be combinable, so a number or a string, and then I want to return A plus B. Now, we saw in the past that this does not work. Instead, we now need to check if type of A is equal to string, for example, or type of B is equal to string. And if that is the case, we return A to string plus B to string. So we concatenate these two strings. Otherwise, if we don't make it into this if statement, we return A plus B like this, because now TypeScript knows A and B have to be numbers here, because if at least one of them would not be a number, we would be in here. Now, this here is called a type guard, because it allows us to utilize the flexibility union types gives us and still ensure that our code runs correctly at runtime. Because often you have functions that work with 2 or 3 different types, and therefore a union type is perfect. But what exactly you do with the values then does depend on the type. Like here, where we either concatenate or we add mathematically. Now, this is a type guard using type of. You can also write other kinds of type guards. And for that, let me come back to my admin and employee types I got up there, where I got privileges on the admin and start date on the employee. Now we have the elevated employee, which combines both. Now I'll also create another type here, and that's the unknown employee. This is either just an employee or an admin. So we have a union type using my 2 custom object types. So unknown employee is either of the 2. Now we might have a function, print employee information, where I need to pass in an employee, and that should be of type unknown employee. Now here I want to console log various pieces of information about the employee. For example, the name from emp.name, which will work without issues because both types of employees have a name property. But then I also want to console log the privileges by accessing emp.privilege. And here I already get problems in the autocompletion because TypeScript can't confirm that this always exists on the argument, because the unknown employee might be a normal employee which does not have a privilege property. Only the admin has that. So now we need a type guard here. The problem just is with type of will not win anything. If we check the type of employee, that will just be object at runtime. That doesn't tell us whether it has this property or not though. Hence, if I move the code in this if check, TypeScript is not happier than before. Because an object is, well, just an object, doesn't tell us anything about the properties. We can't check if it's of type employee because that is not a type JavaScript knows. And keep in mind that this check runs at runtime and uses JavaScript. So we can only compare the type of gets us with the types JavaScript knows. And that would be object, string, number, and boolean, and so on. And our custom type is not part of it. That only exists in TypeScript world, not in the compiled JavaScript world. So therefore, this also does not work. Now here, a workaround is to use a different if check. We know we want to access privileges, so we could check if employee privilege is a thing. The problem just is TypeScript doesn't allow us to access this property at all, not even to check it like this. But there is a different way for us to check it. We can use the in keyword that's built into JavaScript. We can check if privilege, now written as a string, is in emp. This is JavaScript code that allows us to check if this exists as a property on employee. And if that is the case, TypeScript detects this check here and therefore allows us to access this property inside of this if check here. And we can repeat that for the start date and therefore check if start date is a property here. And we can therefore also output this in this if check. So now with that, if we call print employee information and we pass in that one employee we created, E1, you'll see that this compiles without errors and indeed outputs the privileges and, well, also here the date. I should just also say start date here, of course. But with that, it gives us the output we would expect. And on the other hand, if we pass in an employee which does not have all these fields, for example, if we create one on the fly, which only has a start date but no privileges, then this also works and compiles without errors, and we simply don't print anything about the privileges because of this if check we have in there. When working with classes, you can also use another type of type guard, and that would be the instance of type guard. Let's say down there we have a class car, and that has a drive method where I just say console log driving. And we have another class truck, which also has a drive method where we maybe say driving a truck, but we do have the same method name, and where we also have a load cargo method where we have an amount, which is a number, and then here I'm just having some dummy code where I say loading cargo plus amount. Something like that. Oops, amount. Something like that. So now we have two classes, which of course have some similarity, the drive method, but also have a difference. Now again, we can create a union type here, vehicle, which is either a car or a truck. And now let's say we create a new vehicle, V1, which is a new car, and another one, V2, which is a new truck. Now I have a function, use vehicle, which just expects to get a vehicle which should be of type vehicle. So which should be of this union type. So here we get a vehicle, and now let's say our goal here is to do everything we can do with vehicles. Drive and load cargo. So of course we can call vehicle drive because that always exists. But for vehicle load cargo, we have a problem because only a truck has that. A car doesn't have it. So this won't work. Now we can of course again check if load cargo is in vehicle. And if that is the case, we can use it. At least if I fix that typo here. So if we now save that and we then call use vehicle and pass in V1 and then we call it again with V2 and I save all of that, it compiles and it works. Now that is one way of doing it. An alternative way, which might be a bit more elegant because it also eliminates the risk of you mistyping in this property string here, is that you use instance of. We can check if vehicle is an instance of truck. If that's the case, we know it will have a load cargo method. An instance of is a normal operator built into vanilla JavaScript. So this is no TypeScript code. Just like type of, this is part of JavaScript and it executes at runtime. JavaScript doesn't know the truck type, but it knows constructor functions, and classes in the end are just translated to constructor functions. And TypeScript is then able to find out if vehicle was created based on the truck constructor function. So since classes are compiled to something JavaScript understands, constructor functions, it is able to use that. If we would be using an interface here instead of a class, and therefore of course we couldn't have the implementation in here, but would do that when we create an object with the object literal notation, then we could not use instance of, because interfaces, as you learned, are not compiled to any JavaScript code, and therefore we can't use them at runtime. For classes, we can do that because JavaScript supports classes and constructor functions, and with instance of, you can then find out if some object is based on that class. And we know if it is, that it will have a load cargo function. So these are type guards. In the end, type guards is just a term that describes the idea or approach of checking if a certain property or method exists before you try to use it, or if you can do something with the type before you try to use it. For objects, that can be done with instance of or with in. For other types, you can use type of. And therefore, you now have all the flexibility to use the flexibility union types give you and still write code that then does one thing or the other based on the exact type you're getting at runtime. Now, a special type of type guard, you could say, or something that helps you with type guards, is the discriminated union. Now, what's that? It's a pattern which you can use when working with union types that makes implementing type guards easier. It is available when you work with object types. Let me show you how it works. Let's say we have a couple of interfaces, and this could be classes as well, but here I'll go for interfaces to show that it works with those as well. And there I have my bird, which has a flying speed, which should be of type number, let's say. And I also have my horse, which has a ground speed or a running speed, which should be of type number. So we have these two interfaces here. Now we create our own union type, animal, which is either a bird or a horse. And just as before, we might have a function, move animal, that takes an animal as an input, which is of type animal, so using our union type. And now in there, I want to say moving with speed. And now, of course, I need to access either flying speed or running speed. Now, of course, we could have just named it speed, but this is just a simplified example of a real use case you might face where you have some interfaces or objects in general that are kind of related but have different properties or methods. So here it's the speed property, which actually is different. So I can't access flying speed here because, of course, not all animals have a flying speed. Now we can do what we learned before. We can check if flying speed is in animal here. And if that is the case, we can execute this code. Now this is an approach we can take, but the more potential animals we get there, the more things we have to check. We also can mistype here in this string. We can forget an E, for example, and wonder why this won't work. Now we can't use instance of here because I'm working with interfaces. As I explained, animal instance of bird will not work because that is an interface which is not compiled to JavaScript. So at runtime, this will not be available as a constructor function. So therefore, this does not work. Now we can build a discriminated union here by giving every interface, so every object which should be part of that union, an extra property. You can use any name you want. Often you use kind or type here. I'll go for type and name this bird. Now important, we're creating an interface here. So this is actually not a value for the type property. This instead is a literal type, as you learned, where type must hold a string which must be bird. So this is a type assignment where we narrow down the value that may be stored in type to exactly this string value. And I do the same for horse just with horse as a literal type. Now here in our function, we can use a switch statement and switch on animal.type. Every animal has a type property because we added it to all interfaces that make up our animal. And then here we can have a couple of cases where we even get autocompletion because TypeScript and our IDE understands that type can only either be bird or horse. And if it's bird, then we could set some internal variable speed to, let's say, animal.flying speed, and then break thereafter. Otherwise, if the case is horse, we set speed equal to animal.running speed. And thereafter, we can console log moving at speed plus speed. And if I now call move animal with an animal I create on the fly here, where I set the type to bird, and I'm only allowed to use bird or horse, then I have to set my flying speed. And by the way, TypeScript even recognizes that I can't set running speed here. If I try to do that and set this to 10, it complains that this is not available for type bird. If I set it to flying speed, however, it works. And if we save that, it outputs this correctly and also compiles without errors. Now, this is a discriminated union because we have one common property in every object that makes up our union, which describes that object, so that we can use this property that describes this object in our check to have 100% type safety and understand which properties are available for such an object and which properties are not. So this is another useful pattern which you can use when working with objects and with union types. And it even works with interfaces because this interface forces every object you build based on this interface to have this type. So instead of checking for the existence of a given property, or instead of using instance of, we use a property we know that exists to check which type of object we're working with. We also eliminate the danger of mistyping because TypeScript understands that the only cases we can have here for animal type are bird and horse, and hence it gives us this autocompletion, and if we would introduce a typo, we would immediately get an error. So therefore, this is a very useful pattern when working with objects and union types. So discriminated unions, really useful. Another very useful feature is typecasting. Typecasting helps you tell TypeScript that some value is of a specific type where TypeScript is not able to detect it on its own, but you as a developer know that it will be the case. And a good example for this is if we get access to something in the DOM. Let's say here we have a paragraph in the DOM, only a paragraph, nothing else in there, and it's an empty paragraph. So obviously if we save that, we don't see anything here on the screen. Now we can get access to that paragraph from inside our script here. Const paragraph with document query selector p, for example. Now when we use query selector and we pass in p as a selector, so selecting by the p tag, then TypeScript is actually able to find out, as you can see if I hover over it, that this will be of type paragraph element. Or null, because maybe such an element doesn't exist in the page. But that's a different thing. Let's ignore the or null case for now. The important thing is that TypeScript actually finds out that this is a paragraph element. Now this changes if we select by something else. Let's say an ID. We name this here message output. So this paragraph has an ID of message output. Now we as a developer of course know that we assigned this ID to this paragraph. But TypeScript doesn't know that. TypeScript does not dive into our HTML files and analyze them. So if we now select by that ID here, for example with getElementById, then we see what TypeScript infers is that this is just an HTML element, or null. It doesn't know which specific HTML element that is. Now, for a paragraph, that might not matter too much. Maybe we just want to do things with it that we could do with any HTML element. For example, access its text content or anything like that. But what if we had an input here? What if we actually had input, type text, and we want to get the value the user entered. So I'll give it an ID of user input, and now I select this in my TypeScript code. So here I select by ID user input, and it's no longer a paragraph, but user input element. Now we as a developer, we know that here we reach out to this input element. But as I said, TypeScript doesn't know that. TypeScript doesn't read our HTML code, so TypeScript only knows that it's some HTML element. Now if I would want to set the value property of this therefore, and I would try to do user input element dot value equal hi there, you see that I actually get an error. I get an error because for one, this object is possibly null. We can fix this by adding an exclamation mark after this, and I'll come back to this in a second. But even then I still get an error that value does not exist on type HTML element, because this generic type, which basically any HTML element has as a type, does not support properties that are specific to, well, specific HTML elements. So we would need to tell TypeScript that actually what we select here is not just not null, but that it's also of type HTML input element. And that's what we can do with typecasting. Now there are two ways of typecasting, two syntaxes we can use, and they are equivalent. One is that we add something in front of the thing we want to convert, or where we want to tell TypeScript the type. We add angle brackets, opening and closing, and then between these brackets, the type of the thing after the angle brackets. In this case, HTML input element. And this type is globally available because in my tsconfig file, I am including the DOM lib. With that, TypeScript knows that whatever we select here after the angle brackets will be of type HTML input element, and therefore it doesn't complain anymore. So this is version 1. Let me copy that and comment it out and show you the alternative. This works absolutely fine and you can use this. Now, if you know React, however, you know that there you also have such an angle bracket syntax inside of JavaScript or TypeScript, if you use that for React files, where you write JSX code in your React components. Now, if you don't know React, that might not tell you much. Just be aware that a similar syntax exists in React projects, and there the angle brackets are not used to pass any information regarding the types you're using, but instead they are parsed by some build tools and by React ultimately to know what you want to render on the screen. So totally detached from TypeScript. To not clash with that JSX syntax, the TypeScript team provides an alternative to this angle bracket typecasting. You can also add something after the thing you want to typecast, so after this selection in this case, and that thing is the as keyword. And then here you again add the type to which you want to cast this. So this now tells TypeScript that the expression in front of it, in this case this expression here, will yield a value of type HTML input element. And therefore again we get no error. So this is an alternative, and you can use either of the two syntaxes, whatever you prefer. You just should try to be consistent throughout your project then, so that you don't alternate between these two syntaxes. But with that, you can pass this valuable extra information to TypeScript and make code like this work, even though TypeScript on its own would not be able to find out that this here yields a HTML input element. Of course, since you're forcing TypeScript to use this type, it's your responsibility as a developer to ensure that whatever this expression yields will be of that type. Otherwise, you might get a runtime error or unexpected behavior at runtime if you try to interact with that element in a way that actually is not supported. So typecasting is a powerful feature, so is this exclamation mark here. I actually did explore this a little bit earlier in the course already. This exclamation mark allows us to tell TypeScript that the expression in front of it will never yield null. And this is required for some expressions like this here, when we select something from the DOM that might return null. If we know as a developer that this will never return null, then we can use this exclamation mark. Otherwise, and you learned that already, I just want to reiterate on that. Otherwise, if you're not sure that this will not return null, you can use a if check. So you could check if user input element is truthy, and therefore it is not null, and then use it in there. Now, I had to remove the typecasting in this case, because if we do typecast here, we also tell TypeScript that this will not be null. And since I'm not certain about that, I can't cast here. Instead, I have to do that here when I use the value, and therefore I want to do it before I access the value property by adding as HTML input element like this. Of course, that, however, would fail. This is invalid syntax. We would try to access a value property on an HTML input element thing, and this doesn't even make sense. We simply have to wrap this expression into parentheses then to make sure that this is evaluated first, and then we try to access value on the result of this expression. And now we have that alternative to using the exclamation mark. So now, after all these features where we work with the types themselves, so to say, where we worked on checking types, casting to types, let's come back to features that help us write flexible code. Of course, still related to types. It is TypeScript after all, but not so much focused on just the types and how we can manage them. And for that, I want to start with index types, a feature that allows us to create objects which are more flexible regarding the properties they might hold. Now, what do I mean by that? Let's say you're writing an application where you're validating some user input. So you have multiple input fields, and depending on what the user enters there and which field it is, you might want to store and eventually show different error messages. For example, if it's an email field, you want to check whether it is an email, and if it is not, you want to add a proper error message to some error container. So that's what I'll start with. I will have my interface error container here. And that should be an object, hence I use an interface here, but it should be flexible regarding what it holds. Ultimately, my goal is that with that we can create objects where we have some error identifier, which could be the ID of the input field to which the error belongs, for example, email, and then some error string, not a valid email. And then we have another property, let's say username, and then an error string we might be storing for that input field if the input is incorrect. Must start with a character. Something like that should be stored in that object. The problem with that is I don't know in advance which exact property names I will have in there. You could say, well, we'll have email and username. But for one, I want this to be a flexible container. I want to be able to use it on any form I have in my web page. And I might have different forms with different inputs, with different identifiers. So I don't want to restrict myself to just store email and username errors. And in addition, even if we always had just email and username inputs and we just want to store errors for those, what do we do if just the email is invalid and not the username? Then, of course, in this object, we could store null as a value for a username, but I'd like to just omit it so that we have an object which only holds properties for inputs where we have an error, so that we can also loop through this object with a for in loop to read all the errors we got, for example, and don't have any properties in there which don't actually store an error. So long story short, I need an object where I'm pretty clear regarding the value type. It should be a string, but where I don't know in advance how many properties I'll have and which name the properties will have. And for such a scenario, we can use index types. You define an index type by using square brackets here. Remember, normally we would write a property name here, but now we use square brackets. Then any name of your choice, for example, key or prop, then a colon, and then the value type of the property. And in an object, you can have strings, numbers, or symbols as a property. You, for example, can't use Boolean here. That's not allowed. But you can use string here. With that, I'm simply saying that whatever object I'm constructing based on this error container interface later must have properties which are strings. Username, for example, would be a valid string, even if I don't wrap it in quotes. Then we add a colon, and then the value type, which is string. So with that, I'm saying I don't know the exact property name. I also don't know the property count. I just know that every property which is added to this object, which is based on error container, must have a property name which can be interpreted as a string, and the value for that property also must be a string. That's what I'm saying here. Now with that, we also still can add predefined properties, however, only if they're of the same type as this here. So we could add an ID which is of type string, and then any object we build that adheres to this interface must have an ID property and can add as many other properties as it wants. But we can't set ID to a number here, for example, because we have an index type here. So that is a restriction we have if we build such an object. So now what's the consequence? Now we can create an error bag, for example, which is of type error container, which therefore is an object, and it would be valid like this, because we don't have to add any properties. That is also valid. But of course we can now add some. For example, email, not a valid email. And this is okay. It would not be okay if I instead assigned a number here, because we're saying every property needs a string value type. So we must use a string here. If I use a number here, that would work because that can be interpreted as a string as well. So I can also use a number as a key type here if I wanted to. I'm pretty free regarding what I use here. If I would change the prop type here to number, then you can do that and this would be okay. But this wouldn't, because email is not a number. This can't be converted to a number. It can be treated as a string, but not as a number. So this is how you control which type of properties or which property names you allow. And here I indeed want to allow string property names. So anything which can be converted to a string is a valid property name. And then the value has to be a string as well. And as I said, of course, now we can add multiple values here, multiple properties, I should say. Must start with a capital character. So this is now such a error bag we could build with the help of error container, which gives us this extra flexibility that we don't need to know in advance which property names we want to use and how many properties we need. Next, I want to explore function overloads, a feature that allows us to define multiple function signatures, so to say, for one and the same function, which simply means we can have multiple possible ways of calling a function with different parameters, for example, to then do something inside of that function. And a good example where function overloads can help us can be seen a little bit further above. This add function we wrote earlier. What it does is it takes two combinable values, which means strings or numbers, and then as you can see, the return type TypeScript infers here also is combinable. And this simply means TypeScript understands that what it returns also either is a string or a number. But actually, if you think about it, that's not really true. I mean, technically it's true, but we know that if we pass in two numbers, the return type will always be number. If we pass in at least one string, the return type will be string. Now, why might this matter? Keep in mind that the add function is written like this. Actually, we can comment out everything below and add some new code up there right below the function. If I now get my result here by calling add and I pass in 1 and 5, you see result is of type combinable. A consequence of this is that TypeScript does not know whether result is a number or a string. Now this might really matter if we are passing in strings. If I pass in Max Schwartz here, then this works, but I still get back combinable. Now, as a consequence, I can't call string functions on result. I can't call split, for example, to split on the white space. I know that this will work because I know that when I call the function like this, I will make it into this if branch and I will get back a string. So I know that result will hold a string, but TypeScript just knows that it holds a string or a number. Now, of course, we can use typecasting here and tell TypeScript that what we get back is a string. We can do that with the typecasting syntax you learned about earlier. Still, it's not optimal that we have to do that, I would argue, because we have to write more code here, even though we would expect TypeScript to understand that when we call this function like this, we always get back a string. But TypeScript isn't really analyzing our code good enough here. And that's where a function overload can help us. A function overload is written by simply writing function right above your main function, so to say, with the same name. So you repeat this line here, basically. However, without the curly braces, no opening and closing curly braces thereafter. And now here, you want to use specific types, number, and then define the return type for when this is the case, when you get at least one number. And there we could say, then the return type is number. So now with that, we're saying to TypeScript, if we call this function and both arguments are a number, then this function returns a number. Now this, of course, is not syntax that would work in JavaScript. It will be eliminated by TypeScript in the compilation process. But TypeScript merges this function information and this function declaration here together and basically combines the knowledge of these two lines here. And now it knows, okay, we can call this function here either with a and b of type combinable or with a and b of type number. By the way, you also can add more or less parameters here in your overloads. You're really flexible there. We could also add function add here and just expect one number and return a number. And this would also work if we make b optional in our other overloads as well. Because ultimately, of course, you need to ensure that your code in here always works and you receive all the arguments you need in the end. So if b would be optional here, then you see this works. Now, of course, we just would have to work around b being potentially optional down there. I don't need that, however, so I'll get rid of that and just leave this. But I also now want an overload for when we call this with strings. So I will add another add function overload here, where a is a string and b is a string. And then I'm pretty clear regarding the fact that what we return will be a string. By the way, it is a good practice to add a semicolon after these overload lines here. So now with that, I'm saying if we're calling this function with two numbers, we always get back a number. If we call it with two strings, we always get back a string. If we call it with one string and one number, we technically also always get back a string, but I don't want to add all these possible combinations here. Of course, I could add more and then also add number here, or the other combination we might have, which is this one. Well, I guess now I did add all combinations. And now I'm listing all potential combinations of values here and what we return in each case. Now with that, you see the error down there is gone because now TypeScript knows that result will be of type string if we call add with these two values, which are both strings. And if I hover over add, you see there are 3 additional overloads available. Here I'm calling add with two strings, but TypeScript knows there are 3 other ways of calling this. For example, with a string and a number, in which case I get back a string, with a number and some string, or with two numbers. This would also work. Then, of course, I can't call split because TypeScript correctly identifies that when I call this with two numbers, I get back a number, and on a number, you can't call split. So these are function overloads, and they can help you in situations like this here, where TypeScript would not be able to correctly infer the return type on its own. Here, you can be really clear about what's getting returned for the different combinations you might support in your function. Let's step away from function overloads now, and let me introduce one other very neat feature. And that is optional chaining. Let's say you have an application where you're getting data from a backend and data from a database or from any source where you don't know with certainty if in an object a certain property is defined. Let's say we have fetched user data, and fetched user data could be an object about a user we fetched. There we might have an ID, we might have a name, Max, and we also might expect another property, job, which is an object which has a title and which then also has a description, my own company. Now, if we get data like this, of course, we can work with it. Now, you might do more complex things, but here for a start, let's say all I'm doing is I'm actually outputting the job title here, right? Now if we save that with our development server up and running and compilation running in watch mode, I get CEO here. Now thus far that's not too fancy. However, if we are fetching this from a backend, for whatever reason, maybe we don't fetch all the data we need. Maybe some data is not set at this point. In bigger, more complex applications, you certainly sometimes work with structured, with nested data where you don't know with certainty if some property on an object is set or if it's maybe undefined. So here, let's say job does not exist here. For whatever reason, we're not fetching it. Here, of course, I get an error now. TypeScript complains about this because it knows that there is no job property now. The problem is it knows for this data, it wouldn't know if that were data we're fetching from some file that's not controlled from TypeScript. Or, as I just said, if we're maybe fetching this from the backend and we don't know with certainty which data will be returned. Now, if we wouldn't know whether that's defined or not, what we can do in regular JavaScript is we can try to access job, and if that works, we continue and we access title. This is the JavaScript way of checking whether something exists before we then dive deeper into that potential object. And if that is undefined, this code never runs, and hence we avoid a runtime error. Again, here TypeScript of course knows that job does not exist, but if this would be fetched from some source where TypeScript can't look into, like the result of a HTTP request, this would be the secure way of avoiding runtime errors in JavaScript. Now, if this does exist, we get the same output as before. If it does not exist, we don't get a runtime error at least. With TypeScript, you actually got a nicer way of doing that. You got the optional chaining operator. You can add a question mark after the thing you're not sure whether it's defined or not, at least if you're using TypeScript version 3.7 or higher. Here my IDE doesn't like this, but this is a supported syntax then. This tells TypeScript, does this exist? If it does, access job. And hence here we can also add a question mark and therefore only access title if job is defined. Now, if we do that, I still get an error here if I try to compile that, because TypeScript still knows with certainty that job does not exist. But if it wouldn't know that, or if I comment this in, this compiles just fine and also executes as before. So this optional chaining operator here helps us safely access nested properties and nested objects in our object data. And if the thing in front of the question mark is undefined, it will not access the thing thereafter and therefore will not throw a runtime error, but instead it will just not continue. So behind the scenes, this is basically compiled to a if check, which checks whether that exists before it tries to access this. Now, loosely related to optional chaining, we got another nice feature in TypeScript which helps us deal with nullish data. And that feature is called nullish coalescing. Now, imagine you have some data, some input, where you don't know with certainty whether it's null or undefined or whether it's actually a valid piece of data. For example, user input could be null, let's say. Now again, here we hard code this into TypeScript, hence TypeScript knows that this is null. But if you're fetching this through some DOM API where you don't know it with certainty, or if you're getting this from a backend, then you might not know in advance, and TypeScript might not know whether this is null or not. If you then want to store this in some other constant or variable, like stored data, you might want to make sure that if it is null, you store a fallback value. Now you can do so with the logical OR operator, where you store a default, where you get the second value if the first one is undefined or null, if it's falsy to be precise. The problem with this approach is if this is actually not null or undefined, but let's say an empty string, it is treated as a falsy value, and therefore that default fallback value will kick in. So if I console log stored data here, you will see that this prints default. Now maybe that is what you want, and in that case this is a perfectly fine solution. But if you want to keep that user input or whatever data you're working with, unless it really is null or undefined, then you need another approach, because here we would treat this as false and use the fallback. But maybe you want to keep an empty input, just null or undefined should be handled differently. For that, TypeScript also has an operator, the double question mark operator. This is called the nullish coalescing operator, and it means if this is null or undefined, and really just that, not an empty string, not 0, really just null or undefined, then we'll use the fallback. If it's not null or undefined, we'll use that value. So in this scenario here, this compiles, and you see we stored the empty string, hence I'm not printing anything here. This is the empty string. If this, on the other hand, let's say is undefined here and I save this, you say now it says default, because thanks to this double question mark operator, we fall back to this, well, fallback. And therefore here we got another very useful feature which can help you deal with nullish or undefined values with grace. And this is it for this module. We had a look at some advanced TypeScript features that can come in handy in applications. And like with all the other concepts you already learned about, of course we will have a project where we see many of these things in action, so that you don't just learn them here in theory, but you also see them applied in a real project. Nonetheless, I hope the concepts taught here are pretty clear, and their use is clear as well, and why you might want to use some of these patterns, because features like intersection types, function overloads, type guards in various variations with different approaches to find out which type something has, the discriminated unions pattern and so on. These are all interesting patterns that can help you improve your code quality, and make your intentions clearer. Typecasting can be super important to get proper TypeScript support and make sure that you can really work with TypeScript in the best possible way and get the best possible type checking. And with that, let's move on to other modules and see what else TypeScript has in store for us. As I mentioned, we'll of course also see many of these concepts being applied in a real project and in general throughout this course. In this module, we'll dive into a concept called generics. Generics exist in TypeScript, not in vanilla JavaScript, so there is no real translation here, but we can utilize them in TypeScript. And the concept of generic types also exists in other programming languages. Not in all other programming languages, of course, but in some, for example, in C#. Now, this course, of course, is not about C# though, so let's have a look at what generics are and what they are in TypeScript and how we use them there and why we use them there. Specifically, we'll have a look at what exactly generics are and why they are interesting and helpful. We'll then build our own generic functions and classes, because turns out we can do that. We'll then have a look at generic constraints and what that is and why we would use something like that. And we'll have a look at a couple of special TypeScript types which also typically are generic and which we therefore only really can understand now. So let's see what we got there. For that, again, I'm back in our dummy project setup, which we used over and over again. In there, we can run npm start to bring up that development server. And then in a new terminal window, with the server running in a different terminal window, I'm running tsc-w to start my TypeScript compilation process and keep that up and running. With that, of course, we got an empty page because there's nothing on it, but now we can play around in the app.ts file and get started with generics. And I think it's easiest to understand generics if we have a look at a default type which is built into TypeScript, with which we actually worked a lot, which turns out to be a generic. And that would be an array. Now let's say we have an array of names, Max and Manuel, let's say. So we get two names in there. Then of course the type of the names constant is an array of strings. Now actually, we could think of this as two types being combined. Just as you can have an object with different properties, where in every property you might be storing a different type, an array also is just a thing with different data in it, in this case with strings in it. So we actually have the array type, just an array. And if I would remove the names here and cut them, you would see that TypeScript would infer this to be an array of type any, so with any data in there. Indeed, TypeScript knows the array type. So we could say this here should be an array. But as you see, if I specify it like this, we get an error, even though I can tell you that this array type written like this exists in TypeScript. But we see that it's a generic type and that it requires one type argument. And now that's something we haven't seen before. We never heard about generic types before. Now, this strange notation here, whenever you see something like this in TypeScript, you're dealing with a generic type. A generic type is a type which is kind of connected with some other type and is really flexible regarding which exact type that other type is. Sounds difficult? Well, let's go back to that array example. We know that we want to store an array here. So an array itself could be a type. It's a list of data that on its own already makes up a type, you could say, just like an object is a type on its own, even if we don't know yet which data will go in there. So an array is a type on its own. But an array, of course, stores data of a certain type in there. Now, the array type itself does not care which type of data is stored in there. The array type does not care whether you're storing a list of strings, of numbers, of objects, or of mixed data. The array type really doesn't care, but it does care about getting at least some information. Even if you're telling it, I don't know, by setting this to type any array, it's better than not specifying anything. Now, this is one way of defining an array type, the type of data which is stored in there and then square brackets. The other way, which would create exactly the same type, would be to use that array thing and then these angle brackets. And now between these angle brackets, you specify the type of data which should go into the array. For example, a string. And this here is 100% the same as defining this type here. And of course, here you could also use a union type to say, this array stores strings or numbers, or you use any if you don't want to say anything about the type, or as we just had it, string. So this is a generic type built into TypeScript, a type which is connected to another type where we want to know which other type that is so that TypeScript can give us better support. Because here, for example, if we know that what we store in there will be a string, well, then we know whenever I access an element in that array, I can do string stuff with it. I can call all these string methods, for example, and TypeScript will not complain because it knows, well, this array holds strings. That's the idea of generic types. A certain type, in this case the array type, might simply work better or work at all if you provide an additional information about a type of data that's provided in this array type. And of course, the array type is just one example. Another generic type which is built into TypeScript is the promise type. Now, promises are a JavaScript feature, right? It's not a TypeScript feature. You can create promises in JavaScript. And in case you're not sure what promises are, attached you find a link. A promise can be created by using new promise. Again, this is a constructor function, a class built into JavaScript. And the promise constructor function takes one argument, which itself is a function, which then in turn will get two arguments eventually, a resolve and a reject function. Now these will be passed in automatically to us by JavaScript and the browser. And then in a promise, we can, for example, set a timer. And then in that callback function of that timer, we could resolve the outer promise. So in here, in this callback function, we could call resolve and say, this is done. Now, when we do so, this promise here creates a new object, a promise object, which is stored in the promise constant. Now, this promise constant actually has a specific type. It's of type promise, and then again, you see these angle brackets, because this promise eventually will resolve to something. Now here, it says unknown, because TypeScript is not fully able to understand that we actually will resolve to a string here. But therefore, we could say this is a promise which eventually will yield a string. And we do so by, again, using our generic type. The main type is promise. but a promise, just like an array, kind of works together with other types. An array used other types because it stored data in it, data of certain types, and a promise works together with other types because eventually it kind of returns some data of some type. And in this case, that's a promise which eventually returns a string. Now again, why is that useful? Why is this extra type information useful? Well, if we just had a promise type here, and that would not be allowed, but if we said promise of type anything, which would basically the same as if TypeScript wouldn't know generic types, if it wouldn't have any information about what we get back, well then on this promise, of course we can use then as we can do in all promises, and eventually we'll get some data, but we know nothing about that data. I can't call a string method on it, for example. Well, I can because it's any in this case, but I don't get any particular TypeScript support. I could also try stuff on it, which definitely won't work. For example, if we turn this around and we return a number here, I could still call a string method here because TypeScript has no information about the data this promise will eventually yield. Now with generic types, we give that information to TypeScript. We can tell TypeScript that this promise will eventually yield a string or, in this case, a number, and then TypeScript can warn us here. If I try to save this, it will give us an error because it knows, hey, this promise eventually will yield a number, and you can't call split on that. So we get better type safety with generic types. So you're really flexible regarding what you do with that generic type information. An array knows which data it stores, a promise knows which data it returns. If you build your own generic classes or functions, you might do something totally different in there. But in the end, generic types help you to get additional type information if you got a more complex class or more complex function that does something with the data that's coming in a way where it doesn't really care about the data being of one particular type, but where you want to store the type information of the incoming data to get better TypeScript support whenever you work with your generic type. So whenever you work with that promise or that array. That's basically the idea of generics. So this year, all were built in generics. Let's comment that out. Let's now build our own generic type, or let's use our own generic types. So to get started with our own generics, here below the commented out code, I will start with a generic function. You can build generic classes and functions. I'll show both, and here I'll start with a function. Now let's say we want to have a function which basically merges two objects and returns a new object. So here we could name it merge, and we want to get object A and object B as an input. Now of course we could write this function in a certain way. We could say this is of type object and this is of type object. And then what this function does is it returns the result of object assign, where I get object A and object B. So of course, since we got this object assign method already built into normal JavaScript, we could argue if we really need a merge function, but of course you could be doing additional work here. You could enrich this with extra information, with extra options, and in the end this is just a demo, just an example. So this would be valid. We could call merge here and console log its result, like this, and then pass in an object which has a name key, and a second object which has a age. And if we run that and we save this, here in the browser, indeed, we get this output. So we get this merged object. Now, this works. The problem we have with that is if we try to store this, merge name max and age 30, if we try to store this here, I can't access name on the result. I can't access age on the results on this merged object, even though we know that both will exist. Because TypeScript doesn't know this. TypeScript can't know this. Because we are just telling it you're getting an object, and in the end, TypeScript infers that we return an object, which is correct, but which doesn't carry all the information we could use here. Now, of course, we can always do typecasting. We can tell TypeScript that what we get back is an object where we have a name key and where we have an age key, but that's really cumbersome if we have to do that. So here, generics can help us. We turn this into a generic function by adding these angle brackets after the function name, And then we define two identifiers. Typically you start with T for a type, but you could use any identifier here. Doesn't have to be a single character, but the convention is to use a single character, and typically if you only have one generic type, you name this T. And then you say, well, this generic type here, this is now available inside of this function. So we could say what we get here is of type T. Looks strange. We'll get there, no worries. Now here we get two arguments where we don't know exactly how they will look like. So I will accept a second generic type here, simply by adding a comma in the angle brackets, and then we just continue in the alphabet, and therefore the second generic parameter or type you might be using in a function typically is named U. So we could say this is of type U. Okay, now what does this yield us? Well, a lot actually. As you see with this alone, if you hover over merge, TypeScript infers that this function returns the intersection of T and U. And we could of course also set this explicitly like this, but we don't even need to do that because object assign returns an intersection, and therefore since we return the result of object assign, TypeScript automatically understands that this function returns the intersection. So how is this helpful then? Well, if we now hover over merged object, we see that now with this alone, TypeScript understands that what we store in merged object is the intersection of these two object types. Because it sees that we're passing in these objects, which are of these object types it infers, name string and age number, and that our function returns the intersection. Why is it able to infer this now and not with object, which we had before? Because object is a highly unspecific type. We say any object. And yes, therefore, TypeScript is able to infer that we return the intersection of object and object. But the intersection of two unknown objects is just a new unknown object, which doesn't offer any additional type information to TypeScript. With generic types, what we're telling TypeScript is that these two parameters can and often will be of different types. And therefore, TypeScript is able to understand that we're not just working with some random object type, but that we will get different type data here, and that this function overall will return the intersection of that data. And therefore, TypeScript is able to understand that what we store in here in merged object is such intersected data of these two inputs, because now we're not just dealing with some unknown objects here, but with very specific types. And therefore now if I console log merged object age here, this works without errors, as you can tell. Here I'm printing 30 because of generic types. We're giving TypeScript the extra information that we don't know what exactly the types will be. Sure, there will be objects here, we can tell that, but we don't know if it's an object with a name key, with an age key, with a hobbies key. We don't know, and we don't care. We don't care about the exact object here. We don't want to specify that this has to be of this type, because then all of a sudden, if I had hobbies in there, we would have a problem. So I don't want to be that restrictive. I just want to say this is of any type, which I don't care about, but it's most likely a different type than this one here. And if it would be the same, that would be fine too. But TypeScript understands that we do have specific types here for these two parameters, and that we return the intersection of them, instead of just having any unspecific object here. Now, specifically, the magic here is not just that we tell TypeScript that we got two different types here, but that these types are not set in stone when we define this function, but they are set dynamically when we call the function. So here we're calling the function, and TypeScript infers the types for the two arguments. For T, it basically fills in an object type with an object with a name property, which holds a string, and a hobbies property, which holds an array of strings. And for U, it fills in a type of type object with the age property, where age is of type number. Now, when we call this function again in another line and we pass in different objects, and I store this in a new constant with a new name, then of course different types are filled in for T and U for this function call. You can also specifically tell TypeScript which types it should fill in by adding angle brackets after the function name when you call it, and then you would fill in your own types for T and U. We could tell TypeScript that T should be of type string, for this function call, and u should be of type number. But then, of course, TypeScript would complain about the concrete values we're passing in here, because this clearly is not a string, and if we would fix this, this clearly would not be of type number. So here we could be very specific and say, well, the first argument, or the type t to be precise, for this function call here will be an object type, where we have a name property, which is of type string, and a hobbies property, which is of type string array. And the concrete type for u for this function call will be an object where we have a h property, which should be of type number. And now we would be good and no errors would be there anymore, and this would work, but this is redundant. You can absolutely do that, and it is important to understand that this is in the end what generics are all about, that you can fill in different concrete types for different function calls. But we don't need to do that here because TypeScript simply infers the types of the values we're passing as arguments here. And then it plugs in the inferred types for t and u for this function call. That's how generics work behind the scenes in the end. So we got started with generics, and hopefully it's clear what TypeScript does here. We pass some extra information into the merge function so that we can work in a better way with the result of the merge function. And that's typically what generics are there for. They allow you to continue working with your data in a TypeScript optimal way. Now, in this case here, however, we would have a problem if I pass in, let's say, just the number 30 here. Of course, TypeScript now throws an error because it tried to access the age, but accessing the name would work. Nonetheless, if we save that, it compiles without errors, and if I print the overall merged object, we see what I get back is just hobbies and name in my object. Which makes sense because 30 is a number, and when we pass that as a second argument to object assign, which we in the end are doing here, well then this just fails silently. JavaScript doesn't throw an error, it doesn't complain, but of course it also doesn't merge 30 into the newly created object. You see, there is no 30 in this object. Now, how would JavaScript do so? Because 30 is not an object assign only is capable of merging different objects with each other. So what we in the end want to say, well, we don't care about the exact type, we don't care about the exact structure of the object you're providing here for u and t. But what we do care about is that both parameters, both types, t and u, should be any kind of object, but they should be an object at all times. And currently, we're not saying that. Currently, we're just saying they should be of any type. I don't care. Now, often that's not okay. You want to restrict the types of t and u here, so of your generic types. And you can do that with type constraints. For generic types, you can set certain constraints regarding the types your generic types can be based on. And you do this with the extends keyword here in the angle brackets after the type which you want to constrain. So here we could say extends object. And with that I'm saying the t type can be any object with any structure, but it has to be an object. We can do the same for a u. And if I do that, you see now I already get an error here in the IDE, and if I try to save that, I also get an error in the compiler because the type 30 argument here is not assignable to type object. So that's of course the behavior we want here. Now we're forced to pass in an object again. Whoops, like this. Now we're forced to pass this in again, and therefore we improve this function because now it really works. And we know object assign wants two objects. So in the end, we want to guarantee that we get two objects here by setting certain constraints on our generic types. And these constraints here can be anything. You can refer to object, to string, you could use your own type if you had it, you can also use union types here if you want to. You're really flexible there. You can set any constraints you want, and of course you don't have to constrain all generic types. If you just want to constrain u, you can do that. In this example, it just makes sense to constrain both because object assign wants two objects here. But you're really flexible there. It is important to be aware of that concept of constraints though, because that allows you to work with generic types in an optimal way, which avoids unnecessary errors or strange behaviors as we had it before. So let's continue practicing with these generic types, because I know they can be strange to wrap your head around. In the end, they're really straightforward though. Let's create another generic function, count and print. Now this function should take some argument, some parameter, let's name it element, but the name is really up to you, which should be of a generic type, because I really don't care about the type, at least in certain ways. So let's say we have one generic type in this function, and our parameter is of that type. And that's, by the way, also typical for generic types. If you have a generic function, then often your parameter will be of that type. Doesn't have to be, but often that is how you work with generic functions, as you will see as you get more and more experience with them. So here we got count and print with our generic type here, and the element is of that type. Now what I want to return here is in the end a tuple with two elements, where the first element should be my element itself, and the second element should be a description string. Maybe we name it count and describe, therefore. So here I got my description text, and here I'll say got no value. And I want to use that if we pass in an element which has no length, because my idea with count and describe is that we can pass in an array or a string, and we get back the amount of characters or elements in that string or array. So if we got an empty string or empty array, I want to use got no value. But here if I check that element.length is greater than 0, then I want to set description text to got plus element.length plus elements. We could be even more specific and check if the length is equal to 1 here, and then say got one element, else if element length is greater than 1, we have description text equal got plus element length elements, so that we got the plural form right. Now here, description text is therefore the second element I return here. Now you already see TypeScript complains about the length here, because it's not clear that element has a length. So maybe we should make it clear that it does. We could do so by creating a new interface or a custom type with the type keyword here, but here I'll go for an interface, which I'll name lengthy, which in the end is just guaranteeing that we have an object with a length property, which should yield a number in the end. And then here we can set a constraint and say that t extends lengthy. So we know whatever we get will have a length property, and an array or a string would have a length property. Now here I can console log count and describe and pass in, let's say, hi there. Now this works because a string has a length property. It's not an object, it's a string, but behind the scenes JavaScript kind of converts this to an object on the fly, you could say, and adds a length property when we need it. So therefore we can safely call it like this. TypeScript infers that here we return an array with either a string or type t elements in there. Now I want to have a tuple, so I'll be more specific here and set the return type to be basically an array with exactly two elements, where the first element will be of type t and the second element will be of type string. So now I'm just saying that we return a tuple here, where the first element will be, well, any element of our generic type, and the second element will be a string. Now with that, if we save this recompiles without errors and prints hi there, got 9 elements, because we got 9 characters in there. We could also call this with an array, where we have sports and cooking, and now you will see that we got 2 elements as a description text, or also with an empty array, of course, in which case, if I save that, we got no value. But we won't be able to call this, for example, with a number, because a number doesn't have a length property, and therefore this does not work. So here again, we got our generic function. Idea is similar to the function before. We want to be a bit unspecific about the type of data we get here. We don't really care if it's a string, if it's an array, or anything else which has a length property. We just care about that it does have a length property. And then we want to do something with it because we rely on the length property in our code. So we need to guarantee that we got that. But other than that, we really have no interest in which type of data we're getting here. I don't want to lock this down to a string or to an array, and I don't want to create a bunch of overloads to handle all the different possible types. I also don't want to create a very long union type here, because I might forget types which have a length property, or if I create my own object with a length property, I might not allow for it if I restrict this here to be of type string and array or anything like that. So therefore, I want to be more flexible, and with generic types we can be that. We don't care about the exact type. Here, thanks to the constraint, I only care about the fact that it has a length property. So we got the basics about generics down, hopefully. Now let's dive a bit deeper into constraints, or into one specific type of constraint which we can add. And for that, I'll create yet another function, a generic function, which I'll name extract and convert. The idea of this function here is that we get an object as a first argument, and the second parameter is in the end a key. Now I want to return the value for that key in the object, which we can do with this default JavaScript notation, using the square brackets to access a property in an object, but that's nothing TypeScript specific, that's vanilla JavaScript in the end. Now therefore here we could say that here we want to have an object, and for the key we want to have a string, let's say. Now here I'm getting an error though, because what we don't know here in the end is whether the object we're getting here really will have that key. That's in the end what TypeScript is telling us here with this strange error. For example here, I could console log the result of calling this with, let's say, an empty object, and then name. And here, by the way, I'm calling this extract and convert, because I want to call this without console log and simply say value : plus. But that's just a side note. I'm returning a string here in the end with that retrieved data. But the main problem here is I could call it like this, and I would pass in an object as a first parameter, and then a string as a second. But correctly, TypeScript tells me that in the end, it's not guaranteed that this key exists in this object. Now, to guarantee this, we can again use generic types here. We could say we get a type T, and that will be our object here. We can say extends object. But we also got a type U, our key here, let's say, which in the end has to be a key of our T type though, so of this object. So we want to guarantee that what we get here as a second parameter is a key, is a property of that first type. And for that, we can say extends key of T. And now you see the error is gone here, and instead I got the error down there, because now I'm informing TypeScript here that the first parameter should be any kind of object, and the second parameter should be any kind of key in that object. And here, yes, we're passing in any kind of object, but we don't have a name key in there. This error will only go away as soon as I add a name key. So this is also something what we can use generic types for, with this key of keyword here also, to tell TypeScript that we want to ensure that we have this correct structure. And that's of course really useful, because it allows us to ensure that we don't make dumb mistakes where we try to call this function, which in the end would try to access a property that doesn't exist. So this works, but if I try to access age here, I again get an error, for example. So let's switch this back to name, therefore. Okay, enough about generic functions. We will also use them throughout this course, also in the course project, so that should be getting clearer and clearer the more we work with it. The general idea hopefully is clear by now already. Generic functions aren't everything we can use though. We also got generic classes, and therefore let's see how we would create such a generic class and why we could do that, why that could be useful for us. We could be creating a storage class here. A class, let's say, which has a private property data, which in the end will hold an array of data. And then it has an add item method, which takes an item, and that should be added to data with push, let's say. And we have a remove item method, which takes an item, where we could say this data splice, and then we just need to get the index of item here and splice one element. This is how we can remove an element from an array. And of course, get items, where I return, let's say, a copy of this data, like that, with the spread operator you learned about. Now we can do that, and we're getting a bunch of errors here. We're getting a bunch of errors, now for one, because the name storage is a reserved name, so let's name it data storage. That's easy to get rid of. Now we also get an error here because we're not saying anything about the kind of data we're storing and which type item has here. And that's exactly where we can turn this into a generic class, because we might not care about the type of data. We want to make sure it's uniform data, so it's either just strings or just numbers or just objects, but other than that, I don't care about it. So here we could turn this into a generic class by adding angle brackets after the class name, and then again, T, U, whatever you want to use as an identifier, and add this here as a generic type. Now here we can say this here is an array of type T, so it stores data of that generic type in it. Therefore here we add such data and we try to remove such data here. And therefore here get items correctly is inferred to return an array of generic types. And now we can create different storages. We can have our string or our text storage here by calling new data storage, setting that generic type to type string here, and then here in text storage I can call add item, and if I try to add a number I get an error because I'm saying that this will be a data storage which only stores strings. So I can indeed store max here and maybe also store manu, and then call text storage remove item max, and then console log text storage get items. And this should all work if we save that, because it's a generic type, and indeed at the end we just have manu in there. So this would be one simple generic class we can create. Now why would we build such a generic class? Well, just as I said, because maybe we don't just want to store text. I might also want to store some numbers in a different data storage. So then I could create such a data storage, and setting this to number ensures that now we can only add numbers to that storage. And of course we could also set up a storage where we allow both by using a union type. So we got full flexibility there, but we give TypeScript some extra information that makes this both a flexible and still strongly typed class, just as we had it with functions. Really flexible and still perfect type support. That's the whole idea behind generic types. So here we can do that with the data storage class by storing strings or by storing numbers or whatever we want. We'll have one problem about our data storage class though. Let's say here I have my object storage. Now I can create new data storage and say in there I want to store objects, right? I want to store objects, and therefore of course we can go to object storage and add an item, let's say an object where I have name max in there. Now let's also store another object where I store manu. Then let's say we're doing some stuff in our code, and at a later point of time here I want to remove the item. I want to remove the item with name manu here. And then I want to console log object storage get items, like that. Now if we save that, we see we got an object in there that's max. So that looks good, right? Now, it's not really good. Let's say here, I want to remove max now. So now we should have manu left in the data storage. Hence, if I reload, oh well, it's still max. Now, the problem is that we're working with objects here. As you know, objects in JavaScript are reference types. Now, attached you find an additional resource which allows you to dive into reference versus primitive values. Here, I assume you know the difference because it's a core JavaScript thing, totally unrelated to TypeScript. Here, the problem is the way our class is built with this logic on how data is removed and identified. We're not really doing a good job when we work with non-primitive values. So when we work with objects or arrays. Because index auth, if we pass in an object here, will not work because technically this is a new object. It might look like this one, but it doesn't work because this technically is a brand new object in memory and has a different address. And indeed here, JavaScript will look for the address and basically not find it. So what it then does is it removes the last element in the array here. because this in the end returns -1, index of returns -1 here if it doesn't find anything, which means it starts at the end of the array, that's normal JavaScript behavior, and removes the last element of the array therefore. That's why it worked for Manu, it didn't really work, it accidentally worked, but why it does not work for Max. We're always removing the last element of the array for now, since we can't identify it. Now one workaround to at least fix that is to check if we find an item. So we can check if this code here, if that is equal to -1, which means we did not find it, then we can return and make sure we don't accidentally remove the wrong item. But of course now we just fixed that bug, but we still don't have this inner state where it would work with objects. Well, the only way how it could work with objects is if we pass in the exact same object again. So here if I had my max object stored in a constant, like this, and then here I pass in max object, and I do the same here, then I'm really using the exact same object in memory, and therefore now it would work. This would be the only way to make this work. So therefore here, the better idea might be to make sure that this really only works with primitive values. So we could say that t extends string, number, maybe also booleans, and so on. So now we basically say data storage should only work with these types, and therefore objects are not allowed anymore. This might be better here because we would need a more specialized data storage, which then probably only works with objects in turn and not with primitive values, to fine-tune our retrieval logic here to maybe check for some ID in the item that should be removed. The way it works here, it really only works for primitive types, so setting such a constraint is definitely a good idea. And with that, if we save that, after commenting this out, it again works, of course. Now, needless to say, hopefully, that of course, you could have more than one generic type here as well. You're not limited to one type when you work with classes. And you can also have methods which have their own generic types inside of classes. So you could introduce new generic types in class methods if you have some generic type which only is needed in a certain method and not in the entire class. So you're really flexible there. You can use constraints everywhere. And in general, generic types are there to make your life easier and to give you that perfect combination of full flexibility. We can use any primitive value we want here, and type safety, because we know perfectly well what is stored in this data storage and what is stored in this data storage. So this combination is the awesome thing generic types give us. So that is it for generic types already. They can really be tricky to understand, but in the end, the summary I gave you in the last lecture is the perfect explanation. They give us flexibility combined with type safety. We're flexible regarding the values we pass in or the values we use in a class, at least as long as we adhere to the possible constraints which you might have added. But we got full type support for what we then do with the class or with the result of a generic function, because TypeScript then knows which concrete type we pass in when we call the function here, or when we instantiate the class here. Here we then set a concrete type, but we don't lock this class or this function down to that concrete type when we create it. Instead, we're flexible and might just provide some constraints, but of course these constraints also are optional, and you might have some generic classes or generic functions which have no constraints and some which have a lot of constraints. So generic types are a really useful feature. With promise and array, I showed you two of the many built-in generic types. And of course, we'll also see more, including custom generic types, throughout this course. Speaking of more generic types, as a little bonus, you could say, I want to point your direction at a couple of built-in types TypeScript ships with, which utilize generic types, or which are generic types that give us certain utility functionalities. So there's a little bonus here, and from time to time these special types might come in handy. Now attached you find a link to the full documentation of all the built-in utility types. Here I just want to give you a few examples. Now, just as all these type things, These types only exist in TypeScript world and therefore only prior to compilation, but during this compilation step, they can give you extra type safety or extra flexibility. For example, there's the built-in partial type. Let's say we have a new type, a new interface which we define, or a custom type, really doesn't matter, course goal. The course goal does have a title, which should be a string, and let's say a description, which should also be a string. Maybe we also have a complete until property, which is a date. Now we want to have a function, let's say, create course goal, which creates us such an object. Of course, we could have created a class as well, but we have such a function because in that function we might be drawing in some data from a database or whatever it is. So we have this function, and in the end here, I want to get my title, which is a string. I might get my description, which is a string, and I hopefully get my date, which is a date. Now in that function, of course, we could return an object where we just set up all these things. So where we set title to title, description to description, and complete until to date. We could do all of that. And if we then defined that this function will always return a course goal, we would have a correctly set up function. Now, for some reason, let's say we're not doing it like this, though. We're not doing this all in one step. Instead, what I want to do is I want to start by creating a variable here, which holds an empty object. And then step by step, I want to add my title here. I want to add my description here. And I want to add my date here. Now here I'm getting errors because of course I can't set title. This is not a property of this object. And whilst this works in vanilla JavaScript, TypeScript doesn't really like that on the fly adding here. So we might want to say that this should be of type course goal here. Now TypeScript is not complaining about this, but about the fact that this is an empty object, which clearly is not fitting our type here. So in the end, I want to return it and I want to add all these things step by step, maybe because we have extra validation before each step and therefore want to add it like this. Now here's where the partial type can come in handy. We could say that course goal here should be a partial type, which in the end, thanks to generic types, will hold a course goal. Now what this does is it tells TypeScript that this is an object which in the end will be a course goal. But initially, partial kind of wraps our own type and changes it to a type where all these properties are optional. That's what partial does. One of these built-in types TypeScript ships with. So it turns this into a type, which is also an object type, where all the properties are optional. Therefore, we can set this to an empty object initially and still add all these things step by step. The only problem is that in the end, we can't return this because now it's still of type partial course goal and not of type course goal. We can fix this by converting this to course goal with typecasting because we know at this point of time we will have added all the data, so it will be a real course goal and not a partial one. Now, of course, this is a bit made up, but you could have scenarios like this where you want to temporarily switch one of your object types, one of your interfaces, to be optional only, to make sure that all the properties in there can be optional, only temporarily, and then the partial type would allow you to do that. Another built-in utility type which you have is the read-only type. That can also be very useful. Let's say we have an array of names, and in there I got Max and Sports. Now correctly TypeScript infers that this is a string array. Now what can we do? We can of course push menu on there. And probably I should change this to Anna and not Sports to have a name in there. So this works. Now let's say, however, I want to make sure that this is a locked array. We can't add more here. Now we can always add more here, but at least I want TypeScript to yell at me if I try it. Well, that's where we can use the read-only type. We could set this to read-only string array. With that, we tell TypeScript, well, what we store here is an array of strings, but it's also an array of strings which is read-only. So when we try to add something with push, or if we try to remove something with pop, we get errors because we're not allowed to do these things with this array. And this is not limited to arrays, by the way. You can also use read-only on an object, for example, to mark it as read-only so that you're not allowed to change the properties or add new properties to this object. So this can also be very, very handy and give you more flexibility or be more precise about what you're aiming to do in your code. Now, all these are just utility types that only exist in TypeScript world, so they're not compiled to anything, but during compilation, they give you extra strictness or extra checks or skip certain checks as we did it with partial. Now, you got more than read-only and partial, and as I mentioned, attached you find the documentation to a full list of these utility types. In certain scenarios, they can come in really handy, and therefore I definitely did not want to hide them from you, but instead, you should be aware of them so that you can use them when you need to lock something down, or, as in the case of partial, open anything up, or with all the other ones, which I didn't discuss here, if you got some other operation which can be enhanced with one of these built-in utility types. And these utility types are all generic because what they do is they take some other value which is of any type and do something with it. They set everything to optional. They lock it down, not caring about whether this is an array or object or an array of strings, array of numbers, and so on. That's why these are generic. And together with the other built-in generics we saw earlier and your own generics, this now hopefully also again helps you understand why generics can be useful and why they exist. Now, one common source of confusion I want to clarify here is the difference between generics and union types. Why could you confuse these two? Well, for example, our data storage here. If we're accepting generic types based on these types, we could also rewrite that to just say, well, we want to store strings or numbers or booleans in here, right? So we could store that, or to be precise, wrap this in parentheses so that we say either of these types as an array. And then here, of course, we could also say, well, what we get here when we add an item is either a string, a number, or a boolean. When we remove it, it's the same. Now, what's the problem with this approach? On first sight, it might look like it achieves the same, but actually does something totally different. What we're saying here is we're storing any kind of data in there as long as it's either an array of strings, numbers, or booleans. And we're also then adding any kind of data here, either a string, a number, or a boolean, and the same for removing. Now, we already got some errors down there, of course, because I can't initialize this in a generic way anymore. But other than that, it works. Now, the problem, however, is for one up here, we're not saying this is either an array of strings or an array of numbers or an array of booleans. This says, well, we got an array which can have strings, numbers, and booleans mixed. So if we would want to say either an array of strings or an array of numbers, we would have to say string array, number array, or boolean array. Well, we can do that, but now we get a problem here. Now we're adding a string, a number, or a boolean, but depending on what we actually set this data array to be, either a number array or a boolean array or a string array, we're not allowed to add a number or a boolean or a string. If we set this to be a string array, well, then we can't add a number here. Yet here I am fine with any parameter as long as it is a number, boolean, or string. So the problem is here with union types, we accept any of these values every time this method gets called, or this method. So we're not saying, hey, whenever we're working with this class, you have to decide for one type and then stick to it. Instead, we're saying whenever you're calling this method, you're free to use any of these types. And that's exactly not what we want here. If I revert this to the previous setup where we used generic types, then we got a different setup. Here we say you gotta choose once which kind of data you want to store, and then you're only allowed to add that exact type of data. So here, if I add a number, for example, I get an error because that's not a string, and I chose that I only want to manage strings here when I set the generic type. And that's the difference between union types and generic types. Union types can be great if you want to have a function which you can call with one of these types every time you call it. Generic types are great if you want to lock in a certain type. Use the same type throughout the entire class instance you create. Use the same type throughout the entire function. That's where you want a generic type. You want union types when you are flexible to have a different type with every method call, with every function call. Then you can use union types. Generic types lock in a type.